Okay, in this video we're going to be looking at Matlab, and specifically the first thing we're going to do is learn how to read an audio file, one that's already been sampled, and then we're going to look at plot spec. This comes from your book, versus the spectrogram. Spectrogram is built into Matlab. Okay, these do different things and we're going to use both, so it's important to know the difference. Okay, so let's get started by thinking about sampling. All right, so let's say we have a signal x of t and it's sampled, and so essentially we get a digital version of that. I would call that x of n because now we just have samples instead of values for all t. All right, so what we know is that when we sampled, the spectrum of the signal got replicated. Okay, so if it originally looked like this, okay, and we're going to be looking at speech. Speech has a bandwidth of about 4K hertz. All right, so let's pick that up. The first replica of speech would show up right here. So let me first copy that. So the zeroth replica would show up here. And then the next replica would be up at 8 kilohertz, okay, centered at 8 kilohertz, because the sampling rate that we're using in this example is 8 kilosamples per second. So you say that's, we talked about this in class, this is the n equals 0 replica, this is the n equal 1 replica, and so forth and so on. We could paste several of these together and they would all bump up right against each other. Okay, and of course it goes back in the negative direction as well. All right, so what happens from there is that when you reconstruct the samples to get back into the continuous time world, because we live in the continuous time world, you use a low-pass filter that grabs the zeroth replica. All right, so here's a low-pass filter. We're going to keep all this and we're going to get rid of everything else. Okay, and that'll look like our original signal. All right, because we always do that, because we always low-pass filter to reconstruct, the highest frequency, f max, in a digital signal is fs over 2. All right, so in this case, because we're looking at speech and the sampling rate was 8,000 samples per second, f max is going to be 4K. All right, so now to get to plot spec. Plot spec, think of this as a black box. And what happens inside the black box is it's a numerical approximation to the Fourier transform. Okay, so with the Fourier transform, you integrate from minus infinity to infinity across all time of the original signal to get x of f. All right, there's no breaking up the signal into pieces and taking the Fourier transform of little pieces. You do the whole thing all at once. Okay, so that's what we're going to see coming out of plot spec. All right, so spectrogram is different. When you do a spectrogram, this is a Matlab command. What you do is you take the time domain signal and you break it up into little pieces. Okay, So we have these block sizes. A common block size is 256 samples, but it could be a different number of samples. And then we essentially do a plot spec. We do the approximation of the Fourier transform for each piece. Okay? So the spectrogram is all these stacked together. So, you get the frequency content and the time domain representation of when the frequencies occur. All right, so that's the difference. I'm going to show you some Matlab code that hopefully will help it make sense to you.
Okay, now let's run through some Matlab code to illustrate the points that we were just talking about. Okay, before we get started, you should look at the directory structure here. I've got our class directory here, and then I have the shares folder that I sent you the box link to. Within the shares folder is TB Matlab. If you look in there, there's quite a few, coming down this way, quite a few in files that come with the textbook, including plot spec, the one we're going to look at today. All right, so because you need access to these, you should download the TB Matlab directory to your computer, and then use Path Tool to set up a path to that directory. You see here, I already have that set up. So just add a folder, save that, so you can use that from session to session. Okay? All right, so here are the things I wanted to review in this video. First of all, when I go back here and look in the shares directory, okay, there is some files here, some WAV files that I'd like you to be able to have access to. So you can download those, all right? And what I'm going to do is I'm going to first read the speech WAV file. Okay, so the format of that is you give it the output vector name, and then fs is the sampling rate. And so when I run that section, it should read that, and then you can look, yes, there's y, and then fs is 8,000. Okay, from there, I can use plot spec to look at a numerical approximation of the spectrum of this speech file. Okay, so plot spec takes two arguments. It takes y, and Matlab gives you some help. Y comma ts. All right, so that's the period of the sampling rate. So ts is 1 over fs. So that's different than spectrogram. That's just how the author chose to give it. So two arguments, y, and then the sampling period, which is 1 over the sampling rate. Okay, so when I run that, a plot gets generated. Let me drag that down and resize it where you can see it. Okay, so you can see the time domain plot, and then here is the frequency estimation of that file. You see, we talked about the maximum frequency you can have for a signal sample of 8,000 samples per second is 4,000 hertz. Okay, so this goes from minus 4,000 to 4,000, and you can think of it as that blob kind of shape that we've been talking about in class. So following my mouse cursor here, there's the blob kind of shape that we're talking about. Okay, so you notice it looked at the frequency across the whole time interval, all 9 seconds. Okay, it gets crammed into just a single plot of the frequency. All right, so let's contrast that to the spectrogram. Okay, in MATLAB, the spectrogram takes the signal vector y, and then you give it the block size. Although that's an optional argument, but I usually give it 256, so it's taking 256 samples, and it's doing its own little plot spec of that 256 sample snippet of the vector y. Okay, and then if you give it fs, it will rescale this to it'll rescale the frequency axis back to the analog world instead of normalizing everything. Okay, so let's run that section, and up comes the spectrogram plot. You may have seen some of these before, but this is the speech file as a function of time and frequency. So the blocks are going across this way, so it gets 9 seconds, and then frequency component of speech is going up this way. All right. Well, I want to do one more example that I think helps illustrate the difference between plot spec and spectrogram, and that is looking at this file here called macallan.wave. It's actually my old Macallan phone number, and so let's listen to that. Oh, I didn't play it before. You can listen to speech, sound Y, FS, run that section. It gave me an error because I didn't finish. Let's run that section. Run this section.
Notching and peaking filters are referred to generically as cone filters. Notching cone filters are typically used to cancel periodic interference such as the power.
Okay, so you can load it and then play it. All right, so let's do the same thing with Macallan. And listen to it. Okay, so you may recognize that as the sound that's generated when you press keypads on an old-fashioned DTMF keypad. All right, so of course we used to make phone calls that way, and like I said, this was me pressing the digits for my Macallan phone number way back when I lived in McAllen, Texas. All right, so if we looked at the spectrogram, we'll do the spectrogram first because the spectrogram breaks this up as little blocks of time. So spectrogram Y256 FS. So when I run that section of code, then what we get is a nice picture of the phone digits being dialed. Okay, so a DTMF signal uses 2 different frequencies to represent each digit on the keypad. All right, so here's the 2 frequencies showing up when I press that first number. Okay, so I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 numbers to make a phone number. All right. These are separated in time because we blocked up the signal and look at the frequency component of every block. The way you would interpret this is these really bright colors have more energy. If it's if it's blue, for example, there's really not much energy there at all. So that's how this plot's looking. Okay. Now let's compare that with plot spec. And remember, it's 1 over FS. Okay, so when I run that, I get the time domain plot of the signal, so I can see these are the digits that I'm dialing, but I'm looking at the frequency content across all 11 seconds. So they all get, put up there with no indication of when each one occurred. All right, so there's a difference between plot spec and spec. And spectrogram, the plot spec, it's giving you the whole picture of everything that happened, not a specific point in time, whereas spectrogram blocks up the signal so you get some idea of the evolution of the frequency content of the signal.